Chemical equilibrium. Equilibrium is a concept that applies only to reversible reactions where the products can convert back into reactants. Types of reactions. 1. Irreversible reactions. These reactions go only in one direction. Reactants, products. Example, combustion of fuel. 2. Reversible reactions. These reactions go in both directions. Reactants, products. Example, N2 plus 3H2, 2NH3, tensed. What is equilibrium? In a reversible reaction, equilibrium is the stage when rate of forward reaction equals rate of backward reaction. Concentrations of reactants and products become constant, not equal. The system appears to be at rest, but reactions are still happening. This is why we say equilibrium is dynamic in nature. Perfect. Here's a neat physical equilibrium in chemistry. In physical equilibrium, no chemical reaction takes place. Only physical changes occur, such as melting, boiling, sublimation, and dissolving. Equilibrium is achieved when rate of forward physical process equals rate of reverse physical process. Solid liquid equilibrium. Example, ice, water. At equilibrium, rate of melting of ice equals rate of freezing of water. And liquid gas equilibrium. Example, water, liquid, water vapor, gas. At equilibrium, rate of evaporation equals rate of condensation. This solid gas equilibrium. This happens with sublimable solids, solids that directly change to gas. Examples, iodine I2, camphor, dry ice, CO2, ammonia, NH3. At equilibrium, rate of sublimation equals rate of deposition. Gas solution equilibrium. Example, CO2 gas, CO2 dissolved in water. At equilibrium, rate of dissolution of gas equals rate of escaping out from solution. Characteristics of equilibrium. 1. Dynamic in nature. Even though everything looks constant at equilibrium, the reaction is still happening in both directions. Rate of forward reaction equals rate of backward reaction. So it is not static, but dynamic. 2. Observable properties remain constant. At equilibrium, all measurable properties like pressure, volume, temperature stay constant as long as the system remains undisturbed. 3. No effect of catalyst on equilibrium position. Catalyst does not change the position of equilibrium, but speeds up forward and backward reactions equally, helps the system reach equilibrium faster. 4. Achievable from either side, equilibrium can be reached whether you start with rich reactants or you start with products. Both ways lead to the same equilibrium state. 5. Free energy del G equals 0 at equilibrium. At equilibrium, del G equals 0, 0, no net energy change. Reaction has reached a stable state. Of mass action. 1. 1. Rate of reaction. The rate of a chemical reaction is directly proportional to the product of the active masses, concentrations of the reactants, each raised to the power of their stoichiometric coefficients. For reaction, A plus BB, CC plus DD, rate A square, A Ks B, B star, 2. Equilibrium constant Kc at equilibrium, the rate of forward reaction equals rate of backward reaction, and the ratio becomes constant. Kc equals so frac C qua C, C dot D, D, A qua dot B quid B, where A represents concentration in mole per illo. 3. Equilibrium constant in terms of partial pressure Kp. When gases are involved, we use partial pressure instead of concentration. Kp Pc qua C dot Pd quid D, Pa qua A quid dot Kc. Kp equals Kc quads dot RT, where minus R equals gas constant, T equals temperature, K, but delta N equals moles of gaseous products, moles of gaseous reactants, delta N cases. If NP/Nr, delta N 0, Kp Kc. If NP/Nr, Kc Ko, Kpc. Note, gaseous species are considered for delta N. K sub C sub equilibrium constant in terms of concentration. If only moles and volume V are given. Kc equals frac BB eighth squared A, B minus A equals frac NBB N8 squared dot var minus NB Na equals moles of B and A, V equals volume in liters. Delta Ng equals B minus A equals change P sub equilibrium constant G. 2. K sub P sub equilibrium constant in terms of pressure. If only moles and total pressure P frac NB NTB PT dot PT A equals frac NBB NA squared A, delta Ng, where PT equals total pressure, NT equals total moles of gases, unit of K P at M Hashtag characteristics of equilibrium constant, Kc and Kp. 1. What does K tell us? High K value, reaction almost goes to completion, more products formed. Low K value, reaction barely proceeds, reactants remain mostly unconverted. At equilibrium, all observable properties, P, V, T, become constant. Equilibrium constant expresses the ratio of product to reactant concentrations at equilibrium. Chart 3. Substances not included in K. While writing Kc or Kp, we only include gases, G, aqueous solutions, Aq. We exclude pure solids, S, pure liquids, L, because their active mass concentration remains constant throughout the reaction. Changes in equation and effect on K. Change in reaction, effect on equilibrium constant K, reaction reversed. Reaction reversed, K equals 1 for kk or N. Reaction multiplied by N, K equals K, N, and reaction divided by N, Kp equals K squared 1 over N. K can go at Kc and Kp are constant at a given temperature. They only change if temperature is changed. Other changes, pressure, volume, etc., may disturb equilibrium, but don't change the value of K. Qc, reaction coefficient. What is Qc? Qc, reaction quotient, is the same expression as the equilibrium constant Kc, but Qc is calculated at any time, not necessarily at equilibrium. It helps us predict the direction in which the reaction will proceed to reach equilibrium. Formula. So just like Kc, Qc products raise the number of stoichiometric of fan acants each to the power of their stoichiometric coefficient. Comparing QC with KC condition, what it means, reaction direction, more product, less reactant, QC, KC, less product, more reactant. Forward, QC equal KC, reaction at equilibrium, no change equilibrium. QC, KC, more product, less reactant. Backward, the summary, right, QC, KC, reaction proceeds forward to form more products. QC equals KC, reaction is at equilibrium. QC, KC, reaction proceeds backward to form more reactants. Let me know definitions. Del G, Gibbs free energy change at any moment. Del G dur, standard Gibbs free energy change when all reactants and products are in their standard states, 1 atm, 1 m to 98 K. Q, reaction quotient, concentration ratio at any time. K, equilibrium constant. There's a clear explanation of the relation between del G, G. Key formulas, 1, delta G equal del GG plus RTLN Q star. R equals gas constant equals 8.314 joule mole per K. T equals temperature in Kelvin. Q equals to reaction quotient at that moment. 2, at equilibrium, Q equals K. So delta WG equals G0 equals mean RT ln K. And interpretation, condition of relation, direction of reaction. T equals in a reaction, then Kelvin. QK, delta G 0, forward reaction, Q equals to K, delta G equals 0. At equilibrium, QK, delta G 0, backward reaction. Summary, use del G equals del Mzarki plus RT ln Q to find spontaneity at any point. At equilibrium, use del G 0 equals RT ln K to find relation between energy and equilibrium. Negative del G equals spontaneous. Positive del G equals non-spontaneous. 0 del G equals equilibrium. Least caterial. Things an example. Le Chatelier's principle, least caterial principle. What is it? When a system at equilibrium is disturbed by changing concentration, temperature, pressure, or volume, the system tries to oppose the change and restores equilibrium. Chast 1. Change in concentration. Reactant, reaction shifts forward to use up extra reactant. Product, reaction shifts backward to reduce excess product. Reactant or product, opposite direction to restore balance. HAR2, change in temperature. We always run away from heat energy. For endothermic reactions, delta H means 0. So temperature, reaction goes forward. Temperature, reaction goes backward. For exothermic reactions, delta H 0. Temperature, reaction goes backward. Temperature, reaction goes forward. Also, K increases with temperature in endothermic. K decreases with both temperature in exothermic. 3. Change in volume for gaseous reactions. Special case, volume, pressure. System moves to side with fewer gas moles. Pressure, pressure. System moves to side with more gas moles. Special case, if moles of reactant equals product, no change on volume change. 4. Adding inert gas. At constant volume, no effect on equilibrium. At constant pressure, volume increases follows volume rule, goes to more moles side. 5. Density analogy. Solid liquid equilibrium. Water is more dense than ice. Diamond is more dense than graphite. Under pressure, equilibrium favors more dense phase.